Welcome to my new calculus channel. My name is John Gabriel, and as you'll recall, in the previous video I discussed the arithmetic operations using only magnitudes. And now in this video I hope to show you how those work when we give the magnitudes names through actual numbers. In other words, we measure the magnitudes and we find how to work with those using their names in algebra rather than in geometry. So let's begin. Now, you'll recall that I showed you this diagram here with a circle, right? And I also showed you how you can do multiplication mainly. I showed you this particular feature, but I'll show it to you again just for good measure because I didn't actually spend sufficient time on showing you how the arithmetic operations work, which is what I plan to do in this particular video, which is the next in the series of what your ignorant teachers could not tell you. So let's leave this for a second and look at subtraction and addition, which are the most primitive operators. So we'll see here that we can find the difference by comparing the two objects. And the two objects in this case are the line segment that you see here in light blue and the one in dark blue, whose length is 3/2 and 2/2. And that is only so because the unit here is actually 2 units. If it were 1 unit, then the lengths of the lines are 3 and 2 respectively, okay? But it doesn't really matter what particular unit we choose. The result we get will be consistent. So we see that if we take this blue line and excuse me, overlay it with the dark blue line, that the difference will be 1. So 3/2 minus 2/2 is equal to 1/2. And if we increase this length here, the difference will also increase, as you can see, okay? And similarly, if we want to increase this difference, this line length here, then the difference will also increase. And finally, the difference of the 2 line segments will be 0, okay? So as this gets close to this point here, then we get that line segment. But otherwise, the red portion here gives us the difference. And so you'll say, well, how do we do this particular operation? Well, let's see quickly how we do it. So let's suppose if we have, where's my, oh, I didn't mean to do that. So let's suppose that we have 1/2 minus 1/3, right? Now, by the similar triangles in proportion, we know that we can write this as 1/2 plus 1 plus 1 plus 1 over 2 plus 2 plus 2, simply because 1/2 is proportional to itself, isn't it? And we can also write the third here as 1 plus 1 over 3 plus 3. There's a good reason I've done it this way, because the sum of this and the sum of this is 6, right? So we'd have 3 over 6 minus 2 over 6, which is 1/6, and that is the correct result. Okay, and of course if you were adding them, then that would be 5/6. So adding and subtraction of fractions is very simple. All we need to do is use the proportionality theorem to have the same denominator. And all this is done geometrically in this particular diagram. Now, the next problem, or the next arithmetic operation I wanted to show you was that of quotient and product. Now remember, just as addition is defined in terms of subtraction, multiplication is defined in terms of a quotient. right? So, and as you can see here, it doesn't matter what you do, whether it's a whole number or a mixed number or a fraction, the result will always be correct. So let's make the unit 1 here. So that means we've got, or actually, let's rather do this. Let's say, let's move this down here. This down here, and this down here, and now we've got a third. Let's make this 2/3. Oops, I don't want to do that. I want 2/3. Come on, this pen is very sensitive. Right, 2/3, and let's make that 1/3. So it's going to be 2/3 times 1/3, right? And and 2/3 times 1/3 is 2/9, okay? So this result here, and I just want to turn this off here, subtraction, so we can see what's going on. So this result here, and apparently this isn't exactly a third, so I should actually try and get it onto, let me try and get that onto, oh dear, I clicked the wrong button there. I didn't want to trace. Okay, so now we've got 1, right? And so 1/3 times 2/3 is 2/9, as you can see down here. Okay, and now if, for example, I decide to measure, so, and this is very important because we use one line to measure the other. So 2 measures 1 and 1 measures 2, right? In this case here, the length of this dark blue line is 1/3, okay? And the length of the light blue line is 2/3, and their product is 2/9, which is this red line. So that's 2/3 times 1/3 is 2/9. Okay. Excuse me. So now, which you see the result down here, 2/9, okay? Or 2/3 divided by 3. So if we decide to measure them, we can move this point along. And as you can see, the first one tells us that they have this particular ratio down here. See? This particular proportion. 1 to a half, 1 to a half, okay? And so in 2 steps, we measure this light blue line with a dark blue line in 2 steps, okay? And if we had to go to 2, like so, then we've got 2/3 times 2/3, which is 4/9, And if we go back here again, how many times do we measure that in? Let's see here. So the first one is exactly the same, isn't it? The first measurement. And then we get a 1 for both. And by the time we reach 4, we've measured the one line with the other line. Maybe I'm going too fast, but what you can do is you can actually pause the video and you can download this applet from the link that I will provide in the details section. But more importantly, what I want to do is show you that this works without looking at the actual geometry. So let's go back again to our little notepad and clear it like so. We don't want to save that. And so let's look at an example. So let's take a simple example first, which is, where's my pen? Oh, there it is, which is 2 times 3, right? 2 times 3. Now, we can, because multiplication is defined in terms of division, it's the same as 2 divided by a third, right? Which is the same as 2/1 over 1/3. And we can say that's the same as 2/1 plus 2/1 plus 2/1 all over 1/3 plus 1/3 plus 1/3. Remember, if you do it this way, you have to count the same number on the bottom. And I'll show you a different way where you don't have to care. But this will give you 6/1 divided by 1, right? Because 3/3 is 3 over 3, which is 1, and that is 6. Now, you could have done the same thing here like this. You could have just said 2 plus 2 plus 2 over 1 plus 1 plus 1 all over 1 plus 1 plus 1 all over 3 plus 3 plus 3, which would give us 6 over 1, which would give us 3 over 9, which is the same as 18 over 3, right? And 18 over 3, the same as 6. So when you do this, you can do it to either the numerator or the denominator without bothering about the other. You don't have to do both. But if you do it this way, then you must have exactly the same number of operations in the numerator and also in the denominator. And we can do this the other way, as 3 divided by a half, okay, which is the same as 3 over 1 divided by a half, which gives us 3 over 1 plus 3 over 1 and a half plus a half, and that gives us 6 over 1, which again is 6, okay? And so it doesn't matter which way you do it, you will notice that you will get the same answer. Now, multiplication by 0 isn't defined, because if you had to say 0 times some number, let's say k, then both of these must be true. 0 divided by 1 over k, and k divided by 1 over 0. Now, you might barely get away with this one, but you won't get away with this one, right? Okay, so 0 is not really a number, but it's basically a placeholder or something that's very useful in communicating the value of a measured magnitude. Right, so let's look at a slightly more complicated example now, because I showed you this one here with integers. Well, they're not really integers. They're actually fractions. All numbers are fractions, by the way, whether you like it or not. Now, let's clear this, and I'll show you one more example. Now, how about this one? Let's say you have 3/4 multiplied by 2/5. Now, that again, you need to be able to say, in terms of division, it's going to be this, right? Because division, basically, the division is just this measure that you see over here, 3/4 over 5/2. Division just uses the denominator, this denominator here that you see, to measure the numerator. And multiplication is also the same kind of measure, but with the reciprocal of one of the operands. Okay, so it's either 2/5 or 3/4, which is reciprocal, or we find the reciprocal of those and then do the division. And so in this case here, we can just go ahead and say, draw a big line like that, and just go ahead and do this 6 times. Just add them up 6 times. It doesn't really matter how many times you do it. For example, if you do it this way, you can just stop right there, and you could just say, all right, well, let's just do this here, over 2 plus 2, and this will still give you the right answer. It will give you 9 over 16 and 10 over 4, right? Which is the same as 9 over 40, right? Is that right? I think I've done it right. No, maybe I haven't. All right, let's just see what I've done here. So I've said 5 plus 5, 3/4 divided by 5/2 is the same. Oh, that's 12. I'm sorry, that was my mistake there. It's not 9, it's 12. All right. And then, of course, 6 goes into there. 4 goes into there 3, and 4 goes into there 10, and so we get 3/10, right? So 3/10 is the correct answer, but that's just one way of doing it. I mean, I could have carried on here if I wanted to, like this, and it doesn't matter. I could have even left that one just as it is, and then I would have 3 times. Actually, I have made a mistake here. 3 times 3 is 9. and that's 9 over 12. I'm sorry, I did that wrong. Let me start this again here. Let me start this again here. Okay, I'm just talking nonsense. Let me start again. So I can just say 3 plus 3 plus 3 over 4 plus 4 plus 4 over 5. Over 5 plus 5 plus 2. It doesn't matter how many I do at the top. Now let's see if I can add properly. That's going to be 9 over 12. Is that correct? Yes. Okay, and that's going to be 10 over 4. And of course, this here is going to be 9 on the top, because we multiply the top by 12 and the bottom by 12. And it's going to be 9 over 30. Is that right? And 3 goes into there 3 times, and 3 goes into there 10. So that's correct. And of course, it doesn't matter if we had added another 3 on the top here and another 4 and kept this bottom one the same. We would have had 12 over 16, okay? And of course, 12 over 16 over 10 over 4 will give us the same answer again. Will give us 12 over 40, which is equal to 3/10. So it doesn't matter how many times you do it on the bottom or on the top. But it will matter if, for example, you said 3/4 plus 3/4 on the top like this, and 5/2 plus 5/2 like this, then that would be 6/4, and this would be 10/2, okay? Not the same as what you did on top here. And then again, of course, if you multiply both by 4, then you get 6 over 20, which is still 3 over 10, all right? So now I showed you that this here is just the 3/4 times the reciprocal. Let me use my mouse. 3/4 times the reciprocal of 2/5. And now we'll do very quickly the other way around. That is, we'll do, get my pen back again. We'll do 2/5 divided by 4/3, right? 4/3 is the reciprocal of 3/4. And again, that's going to be 2/5 over 4/3, like that. And it doesn't matter how many times you do it. Let's go here, say about 3 times on the top like that. And 5 plus 5 plus 5, it's actually just 5 times 3. And again on the bottom, 4 plus 4, let's say over 3 plus 3. And that's going to give us 6 over 15. Maybe we should have, to get the same denominator, add this another 3 times, like so. Okay. 3, and we'll get there 20 over 15, which is the same as 6 over 20, which is what we got over there doing it this way. Okay? So, excuse me. I'm sorry about those few mistakes I made, but I did correct them. Now, this is basically how we do all these operations that you see here without looking at the geometry. But we're still using similar triangles, right? In other words, we're still using these results, right? Okay. So we can say, all right, let's do this, bring this down here, like so. And now 2 times 2 is 4, and we're back to this again, which is no problem because we've already seen how that works. And I believe this is the final series that I shall be discussing numbers. All of you should now know how to do arithmetic with numbers and where they came from. They came from magnitudes, and there are no other numbers. So if it's not a rational number, it's not a number. Real numbers don't exist. Now, we do have incommensurable magnitudes, which we could measure using the circle diagram, but then we're not able to actually quantify. So for example, let's say if we had pi, which is about 3.14, something like that, right? And we had 1 times pi, something like that. Oops, let's just do this. Can't really get, okay, it's approximate. At any rate, this red line here would give us the idea of what the magnitude pi is, but we have no measure. And the other thing to note is that if I change the unit, we'd have a different size line. So in all truth, we don't have a precise measurement unless we can describe it using numbers, okay? Because a number is the measure of a magnitude, and I was the first human in history to describe it so precisely and exactly. Yes, you can call me a genius because I am, but I'm not arrogant. It's just a fact. I am. And I was the first to realize the perfect derivation of numbers from what Euclid was attempting to write down, okay? So no academic before me actually understood number, and no one was able to solve the tangent line problem. I don't care how many times you've heard that the calculus was made rigorous. That is absolute bullshit. It was never made rigorous. My new calculus is the first and only rigorous formulation of calculus in human history. And I encourage you to read my free ebook, which is the most important mathematics book ever written. In it, you will find many interesting details, and you will find the truth and what you need to become successful in mathematics. You don't need the garbage of set theory, real analysis, topology, and all that other bullshit. That's totally irrelevant. It's not mathematics, it's mathematics, because mathematics has no ill-formed concepts like infinity and infinitesimals and all that kind of nonsense that you'll find in mainstream mathematics. So I hope you've enjoyed this video, and I'm sorry that I've been coughing, but I'm not well. I promise to give you another much more exciting video in the upcoming weeks. And please click like and subscribe to my channel and pass along the information that you see here on the New Calculus channel. I am the great John Gabriel, the discoverer of the first and only rigorous formulation of calculus in human history. Well, my friends, I hope you've enjoyed that. Till next time, goodbye.